We discussed the origins of the concept of terraforming in the first part of this debate, as well as the need, in the case of Mars, to begin a warming process by releasing the carbon dioxide contained in the polar ice. In this second section, we will examine the ways offered to accomplish this, finishing with an examination of the operation's real practicality. A black powdered substance, coal dust, sprinkled on the polar ice cap might also be used to raise its temperature. This would lower the quantity of sunlight reflected by the ice caps into space, causing the ice to heat up. According to a NASA research, the caps might be completely destroyed in a few centuries. But where to find this black powder? Some speculate that it was sent from Phobos and Deimos, two of the solar system's darkest bodies, or that it was introduced by dark extremophilic microbial life forms such as lichens, algae, and bacteria. However, Mars is already the second darkest planet in the solar system, absorbing more than 70% of incoming sunlight, so the potential for further darkening is limited. And dig thousands of tons of black regolith on Phobos and distribute it on the ice, this can't be a joke. Not to mention more crazier ideas like igniting nuclear reactions within Phobos to turn it into a tiny star. Or to detonate nuclear bombs in the craters of ancient volcanoes in order to reactivate them. Or to alter the orbit of some asteroids such that they collide with the polar caps. Speaking of odd and deadly ideas, Elon Musk recently advocated hitting the poles of Mars with hundreds of atomic bombs in order to liberate all of the CO2 held. A suggestion that, thankfully, NASA quickly rejected, demonstrating that hundreds of explosions per day would be required to achieve any result. In short, the ideas to awaken the globe by raising the temperature exist, but the fact is that these are undertakings that are currently well above our technological capabilities and will likely remain so for several millennia. Terraforming a planet like Mars also necessitates understanding in climatology and planetology, which we lack. Man is unable to manage the Earth's climate now, and we must acknowledge that we suffer from it far more than we control it. The red planet is also hampered by two fundamental disadvantages that might derail any terraforming effort. Mars is a small planet with 1/10 the mass of Earth, and its gravitational field has proven ineffective in keeping a major percentage of its valuable atmosphere from escaping into space. Even if you do manage to construct a dense atmosphere at the right place, the challenge will be holding it back. Mars, unlike Earth, no longer possesses a worldwide magnetic field. The dynamo effect has ended due to the rapid cooling of the metal core, which is linked to the planet's small size. This magnetic field acts as a barrier for Earth, shielding the atmosphere from the abrasive impacts of the solar wind. Pessimists believe that despite their brilliance, humans will never be able to reactivate the Martian magnetic field, despite a study in which Jim Green, director of NASA's Planetary Science Division, proposes to place a magnetic shield dipolar at Mars' Lagrange point L1 to create an artificial magnetosphere around the planet. And the planet will never be able to rely on this formidable natural umbrella to prevent the erosion of its atmosphere. Man will almost certainly have to surrender forever if there is no global magnetic field and gravity is feeble. This is a severe sentence, but suppose for the sake of argument that we have somehow managed to activate the greenhouse effect on Mars, elevating atmospheric pressure to at least 1/10 that of Earth and allowing water to form pools here and there. What should the next step be? At that point, if we ever get there, the strategy is to rely on infantry, i.e. germs. Microorganisms appear to be the best actors for terraforming Mars. As on Earth, they may emit ammonia or methane, gases that are far more efficient in terms of the warming effect than carbon dioxide. Laboratory simulations have previously demonstrated that some methanogenic bacteria can adapt to low air pressure and locate the nutrients they need to survive in Martian soil. Planetary engineers will also be able to take advantage of the bacterium Deinococcus radiodurans' extraordinary resilience. This microbe can withstand radiation doses 3,000 times greater than those that would kill a person and has a strong tolerance to drying. If bacteria cover 1% of the world and their efficiency in converting solar energy into a chemical compound is 0.1%, 1 billion tons of methane and ammonia will be created annually, raising the temperature. Every 30 years, the temperature rises by 10 degrees Celsius. Furthermore, the methane and ammonia created by their metabolism will give good UV protection. Once this stage is reached, the benefits to future settlers will be enormous. The next stage toward true terraforming will be a major change in the atmosphere, introducing oxygen and nitrogen while eliminating carbon dioxide. This is the well-known process of chlorophyll photosynthesis, by which plants on Earth provide oxygen to animals. To improve the oxygen concentration of the Martian atmosphere, we can spread cyanobacteria, which are adapted to live in harsh environments such as Antarctica. Cyanobacteria were among the first living organisms on Earth. For 2 billion years, these organisms ruled the Earth's surface and significantly altered the makeup of the planet's atmosphere. They can progressively modify the composition of the Martian atmosphere by absorbing CO2 and releasing oxygen via photosynthetic activities. So why not? Scientists have focused their attention on 2 especially resistant cyanobacteria species. Crucoccytiopsis is a cyanobacterium that can withstand intense drought, high salinity, and considerable temperature differences. Crucoccytiopsis lives on Earth in deserts, buried a few millimeters beneath the surface of translucent rocks, sandstones, which act as a moisture trap and ultraviolet barrier. The second species, Madii, is a drying-resistant cyanobacterium that can find safety by dissolving carbonate rocks. Madii can also repair atmospheric nitrogen if it is sparse in its habitat. Whatever algal species are chosen for terraforming, they must first raise the oxygen partial pressure to the 1 bar threshold. Higher plants will be able to grow freely on Mars' surface at that time. These plants, which have been genetically engineered to be more efficient, will adapt to the harsh Martian circumstances and produce even more oxygen. As a result, the partial pressure will finally rise above 120 bar. The oxygen level will then be sufficient for the first Martians to leave their respirators in the locker room before venturing out. Using this method, Mars may be changed from its current dry and frigid state into a warm, slightly humid planet capable of supporting life within a few decades. Although the air would not yet be breathable for humans, they would no longer require spacesuits and could instead wander freely outside wearing conventional clothes and a simple mask. Large habitable areas may also be developed beneath massive inflatable domes carrying breathable air, and simple, resilient plants could thrive in CO2-rich soil and spread quickly throughout the surface. Over time, these plants released more and more oxygen into the atmosphere, promoting the growth of more sophisticated plants and the existence of a growing number of animal species. These aren't just theories. Terrestrial lichens found inside the German Aerospace Center's Mars Simulation Laboratory withstood exposure to climatic conditions. They accomplished this by clinging to the gaps in the rocks and empty areas of the mimic Martian soil, adapting and showing the same behavior they would have displayed in their native environment. Could it be that the ideal approach to think about Mars terraforming is through the heavy employment of microorganisms and primitive plants, possibly genetically modified, rather than through violent planetary upheavals? Regardless, a terraforming debate would be incomplete without the question, should we do it? The fact that terraforming is theoretically possible and would not directly destroy an ecosystem does not imply that it must be done. Mars is lovely and fascinating as it is, and we should leave it that way so that future generations can study it. Anyone who can read the billion-year-old Martian landscapes can learn about Mars and the solar system, and their destruction would be a tremendous loss to science. Its desert's cold beauty must be protected. There's also the possibility of biological contamination. If there is microbial life on Mars, the advent of terrestrial creatures or our upheaval of the Martian environment could cause it to vanish. Even if the absence of life is proved, others claim that the rocks and shape of the terrain have inherent value. This is an extreme viewpoint known as cosmic preservationism. The anthropocentrists are certainly much more quick in this regard, believing that everything man needs is beneficial. From this perspective, terraforming Mars is permissible as long as it serves human needs. Regardless of these concerns, terraforming Mars may be an unavoidable event in human history. Our planet, Earth, is vulnerable and isolated. An asteroid strike, for example, might wipe out humanity and its history in seconds. Isn't it the objective of man to wander, discover new worlds, settle, and thrive? Mars is a new world, a new frontier, and the birthplace of a new mankind. According to Carl Sagan, terraforming should not be used to address our planet's overpopulation problem. A one-way ticket from Earth to Mars is too expensive. The similar point is made for mineral resources. It would be too expensive to transport them to Earth. Terraforming raises a plethora of ethical concerns. But one thing is certain, given 22nd century technologies, a dramatic alteration in the conditions governing Mars' surface is possible. Will humans desire to alter Mars' appearance? The question remains unanswered.